Yes, Mira, you can start.
Good evening to one and all present here for the IEEE International Webinar Series SAVANT. I am Meera Ganesh, IEEE Student Chairperson of Robotics and Automation Society from the Department of Electronics and Communication Engineering. On behalf of St. Joseph's Institute of Technology, I am here to volunteer for today's session. Now, I request Dr. C. Jnana Kausalya ma'am, Professor and Head Staff and Students Affairs, to take over and address the session.
Good day, Mr.J.PATRICK, Waddell, and dear participants. This is Dr. Jnana Kausalya from Department of ECE, St. Joseph's Institute of Technology. On behalf of St. Joseph's Management and Organizing Committee, it's my distinct privilege to welcome today's Mr. J. Patrick Waddell, Industry Consultant and S6 ATSC Chair, California, USA. Thank you, sir, for accepting our invitation and to deliver a lecture on hot topic, audio loudness, and how to protect our hearing. Thank you, sir. Thank you very much for accepting our invitation. And also, I take this opportunity to mention our sincere gratitude to our chairman, sir, Dr. B. Babu Manoharan, Managing Director, Madam, Mrs. Jessie Priya, Director, sir, Mr. Sashi Sekar, and Principal, sir, Dr. P. Ravichandran, for their support to organize this webinar series. Also, my heartfelt thanks and welcome to dear participants, and I assure you that this webinar is going to be a powerful tool to improve the knowledge in this domain. Warm welcome to Mr. Patrick and all participants. Thank you. Now the session over to Ms. Mira to introduce our distinguished speaker. Mira?
Thank you, ma'am. Thank you, ma'am.
Thank you. Thank you.
I will be sharing a few words about our speaker. Mr. J. Patrick Waddell is the SMTE Life Fellow and an industry consultant in the area of media standard development and Essex Advanced Television Systems Committee Chair. He serves as a harmonics representative to a number of industry standard bodies, including the SMTE, SCTE, DVB, and the ATSC. He is currently served as the chair of the ATSC's TSGS6, the specialist group on video audio coding, and was the founding chair of SMTE's Technology Committee 32NF on Network Facilities Infrastructure. He is also an SMTE Fellow and the 2010 winner of the ATSC's Bernard J. Lechner Outstanding Contributor Award. His specialties are standard development, intellectual property protection, and licensing and broadcast regulation. Before we start the session, I would like to say a few instructions to be followed by the participants. Kindly post your queries and questions in the chat box. There would be a Q&A session in the end of the session. The attendance link will be posted at the end of today's webinar. Now, I invite our speaker of the day to kindly start the session.
Thank you, Mira, and thank you for inviting me. This is a distinct honor. And let me give you the appropriate BTS boilerplate slides and introduce myself visually. This is 5 years old, but this was holding the technical Emmy that the ATSC was awarded for our work in audio loudness. And we will talk much more about that over the next few minutes. So in updating this presentation, which I have given many times over the last 20 years, I came to realize, gee, we're all now listening on portable devices, and protection of hearing is probably important. So that's now a major topic. One of the things that we need to be cognizant of is the fact that we're dealing with the law of unintended consequences. This topic is a perfect example. So let's begin at the beginning, to use a trite expression, with analog television audio, which grew directly out of analog radio, both AM and FM technology back in the 20s and 30s. It's transmitted, even though different parts of the planet use different scanning systems, that over the year still works the same way. It's FM analog audio and AM modulated video. TV sets, by and large, had tiny little speakers which were mono only, and so even after the stereo-compatible system was devised, the industry, by and large, ignored it. And sadly, in the industry, a lot of the visually oriented people took the sad attitude of it's the squeaky stuff that comes along with the pictures. And you may remember what these look like from your childhood, right? So thankfully, we're done with CRTs. When we got to digital TV, we discovered that it came automatically with 2 channels because it made use of the AES-3 infrastructure, which is a 2-channel infrastructure. And beyond that, as we rolled it out in North America, and I would expect now that it's rolled out in, I think, most, if not all of India, that many consumers will have purchased what are described as home theater in the box sound systems. And so you have a large number of households that actually have 5.1 or more in their living rooms. And the broadcasters are aware of that, and they are accounting for it. So in the conversion to digital, both the video and the audio got significant upgrades. The important other thing to remember about digital audio is that depending upon the bit depth of the samples, you get 96 to 104 or more dB of dynamic range versus less than 40 that we had with analog. And what have the creatives done with this? I live in the San Francisco Bay Area. We have a local station that actually carries occasionally Indian imported programming, so I've actually seen some of the output of Bollywood and heard it. So your creatives are doing what our creatives are doing, and that is running with this ball toward the goal. They eagerly like the dynamic range because it allows them to tell their dramatic stories much more dramatically and with much more impact. So that's good news, and it's also bad news. So we discovered back in the mid-last decade that AES-3 had been published way back in 1985 and did not have any ability to signal operating points or alignment levels. The result of that in the music business has been that the choices by the production community have varied all over the place. And I have some concrete examples that, because I'm a San Francisco Symphony subscriber and also buy their CDs, they've done 3 different recordings out of the several hundred they've done that vary in loudness by at least 6 dB over a decade, and I was puzzled as to why, and now I think I know, and I'll share that with you as we move forward. But what this led to was consumer irritation, because you had no channel-to-channel level consistency, and in some cases, little program-to-program level consistency. Why is that? Well, it turns out that audio is a fairly complex waveform. And if you think about it in its electrical representation, our ears can hear from subsonic to almost ultrasonic, from less than 1/100 of a hertz to 20 kilohertz. And I know parts of India occasionally get earthquakes. We get them here in California. If you've been through an earthquake, you've heard the subsonics. And so while our ears, as we age, typically will lose some of the high frequency detection, most of us started life as children with the ability to hear all the way up to 20K. And this, again, as engineers, this is why we use dBs, because dynamic range is so enormous. we go from, millivolts or microvolts in the case of microphones all the way up to, hundreds of volts in the case of like a studio or stadium audio system. So what does this look like as a waveform? Well, I apologize for this being a fairly old and fairly blurry picture. It was off of an audio analyzer I used to have in my lab, and I didn't have an iPhone to take a picture of that would have been crisper, so this was fairly blurry. It was off of film. But if you note, there's a dotted line up at the top. That dotted line happened to be, for this analyzer, the magnitude measurement, but it can serve as sort of an indicator of where we might be taking sampling points when we do digital audio. And as you can see, the peaks don't always line up with the sample points. So that's another potential problem in digital audio. That's yet another one of our unintended consequences. We discovered as we started using this system that we had this huge dynamic range that no longer had a noise floor that was coupled with the signal like it was in analog. And AES-3, as I had said a bit ago, didn't make any provision to signal your operating point. And eventually in 2003, they added the ability to signal one of three, and that's not adequate. So as the expression goes, too little, too late. So why did that become such a big deal? Because in traditional analog systems, and if you listen to over-the-air AM radio, and I think it's still on the air in India, you typically use what's called a compressor limiter to both squish the loudness down and mostly to protect the transmitters. The audio community describes that as making sausage because you're really squishing the audio. In the case of some pop music, they use that or try to use that, but that's not a desired effect for the audio community. And it turns out that listeners can actually tolerate a fairly wide amount of loudness variation, provided that it's within what came to be characterized as a comfort zone. So we can listen for a given gain setting, and we're happy if it's 2.4 dB loud or 5.5 or so soft. And beyond that, people typically try to reach for the volume knob. But if we keep the loudness range in that area, that's a good, pretty close to 7 dB. That gives us a good operating point. We discovered in doing the ATSC loudness work that the advertising industry was equally unhappy as the broadcasters. And the U.S. has 4 different commercial networks and a public broadcaster, and thousands of individual independent television stations. So the advertisers were out there having to create hundreds of versions of each ad, and that was very expensive and very frustrating. And each of the networks set their own requirements, and they did this, of course, without talking with each other, and it meant that everybody was highly frustrated. This was one of the reasons why in 2006, and yes, this is a fairly long time ago, but it was early in the digital transition in North America. ATSC Board of Directors recognized that audio implementation continued to dog the DTV transition, especially in problems related to audio levels and AV sync. And note, at this point in time, the advertising revenue was not attached to the digital. So this was looking out to where they would be in a couple of years when we made the transition. So they asked the specialist group that I was the chair of, TG1S6, to create a couple of ad hoc groups to address these topics. One of them, of course, loudness, the other AV sync. And so the loudness group got given the, for historical reasons, S6-3 as a title or designator. And they started their work in mid-2007, somewhere in the June-July timeframe. So it's hard to get a lot of traction over the summer with people going on vacations and so forth, but we started. And it took about 18 months to produce what became ATSC's recommended practice A85, which first published in November of 2009. But also in July of 2007, down in Southern California, University of Southern California Center for Sound hosted a Loudness Summit. And if you're a Star Wars nut and have delved heavily into the creation and background of Star Wars, you'll recognize Thomas and Holman's name. He was the mixer for the first three, although they're not chronologically the first three episodes of Star Wars, before he got hired away with George Lucas's funding to create the Center for Sound down at USC. So Tom gathered us together in one of the big lecture rooms down there, and there were a couple of hundred people in the room. And he made some opening remarks where he commented that this was, as he phrased it, a living room couch problem, noting that all of us in the industry sit with our families watching and listening to the content we've helped create, and we endure all the loudness issues along with everybody else. So this wasn't a conspiracy the industry was doing insidiously to make people miserable. And the issues focused primarily on the fact that we had no standards or even guidance to the creative community and to the rest of the operational side. We didn't have an easy method to measure loudness, and we will get into this topic in great detail coming up. And each of those 5 networks were trying in isolation to solve the issue, and that just translated into total chaos because we had 5 different solutions that weren't solutions. So in updating this presentation for today, I realized that the same situation now exists with the portable device you have in your pocket, and maybe either listening to recorded content from or streaming content from. So we're still somewhat in the, as the old expression goes, Wild West. So back, however, to tell the story of how we got to A85. S6-3 had several specific tasks. One of the things you do in standards development is you set out a scope of work for the group. So they were told to make sure that the DTV system would provide a uniform subjective loudness for all the audio content, both across the channels and within the channels. They were asked to focus on spoken word, otherwise known as dialogue, because in that study that had reported in that AES paper, they quickly recognized that's what human beings focus on, is the spoken word. And they asked the group to look at measurement standards and mixing and proper monitoring techniques. And that was Tom Holman's major contribution to the discussion right there, along with several other mixers in the room. And that we also needed to pay attention to getting it encoded and including all the metadata, and not just for the local or network programs, but the commercials, the promos, and everything else. And there was already a part of the AC3 digital audio system that ATSC was using that was called dynamic range control, and people were not always using it right. So that was part of it. So the technical issues, getting back to how we wrestled this thing to the ground, we recognize that volume is not loudness. The traditional audio metering, and if you've ever done any audio work, you've seen what I will call the dancing meters on the front of the console. Those were all nominally instantaneous, but they're hardly instantaneous. In the old days, they were analog meters. They had movement ballistics, and they certainly didn't detect things like digital audio clipping. And by the way, digital audio clipping, which I will not inflict on you, sounds horrible. You don't want to hear clipped digital audio. And now that we know how to measure loudness, it's a time-averaged measurement. It's not an instantaneous measurement. So we needed to come up with a way of measuring where really the true peaks were. And, drilling down a little bit into the traditional audio metering, there was no surprise. North America was different than Europe. The North American meter was developed by Bell Labs back in the 30s, and most of us called it a VU meter. It was officially an SVI. And at about the same time, the BBC had developed something that was widely used in Europe called a PPM, or sometimes QPPM for quasi-peak program meter. Both of these were based on double E's will recognize this rectifier galvanometer pair, the way a typical electrical meter works. And the only difference really was the response times. Also, meanwhile, at Bell Labs in the 30s, there were a couple of guys that were doing research into our hearing response. Fletcher and Munson, and they used headphones for their testing, but they discovered, actually they confirmed, because I guess they started with the suspicion that this was the case, and then through their testing demonstrated it was the case, that humans have different sensitivities to different frequencies, and that were somewhat different at different SPL levels. In the 50s, another set of researchers said, well, they used headphones of what would happen in free space, so they used an anechoic chamber and speakers and repeated the same measurements in free space, and they got similar but slightly different results. And here they are. The red curves are free space. The blue curves were with headphones. So here we begin to enter where portable devices potentially can damage our hearing because of the different ways that we respond to low frequencies. And as I said, we will talk about this in detail. But this is due to the effect of the outer ear, which isn't there just as a beauty thing to attach earrings to. It's important. So again, we begin to recognize that volume and loudness needed to be dealt with as related but different, and that loudness measurements were not going to be instantaneous. They would have to be time averaged. So for operators, and having spent a number of years in recording studios trying to deal with getting stuff on tape, I was used to dancing graphs or bar graphs, and so hearing that I couldn't rely on those anymore was not good news, at least initially. But we also had discovered that the analog meters certainly did not help with the problem of digital audio clipping. So we really needed some instantaneous measurements to avoid clipping. Clipping in the analog domain typically means the signals approaching the power supply rails, and depending upon the circuits involved, that introduces some singing, and there's actually some people built effects boxes that they sold to people, including the Beatles. So on some of Sgt. Pepper, you hear a little bit of the singing from analog clipping on one or more of their cuts. But in the digital domain, it means we've run out of bits. And it really sounds terrible. what historically this meant was that we would back off our operating points. Now, the good news about digital audio is that basically you can move it up and down by just doing math on the samples, because the noise floor is not related to the samples. So that's one of the nice things about working with digital audio workstations, is that we can actually move things around freely without doing damage. But we have a couple of different CDs that I personally was puzzled as to why they were significantly different in level, especially given the loudness in the hall for Mahler's second versus Mahler's sixth. And I will come back to this as we get further down, because it relates directly to sort of the serendipity out of the pandemic. And there is a little, fortunately. But we have another acronym you may stumble into that was all that was available for loudness measurements back in the 80s and 90s. Was called LAEQ, and it had been baked into A53, the ATSC standard, because there was nothing else available. The ITU recognized it didn't work. It really was an industrial noise measurement technology. And so they started back in the 90s. They went through like 25 or 30 different proposals, all of which failed during testing. Finally, a researcher at the Canadian Research CRC Canada Research Center. I have to get my notes.
Sir,
proposed a
sorry to interfere.
Uh-huh.
I'm so sorry to interfere. Could you please increase your audio? The participants are having trouble hearing you. It's just a kind request if you could increase your audio.
I'm talking into the phone. I'll move the headset back. Is this better?
Yes, it's way clear.
Okay. Okay, thank you. So Canada Research Center proposed this really simple power average measurement with an input filter to undo the effect of our hearing boost, and this became ITU recommendation BS 1770. It was the first international standard that actually measured audio loudness, and the initial publication in 2006 just dealt with loudness. They added what was called true peak measurement in 2009. So it uses or creates a measurement in something called an LKFS unit, and that's a mouthful, so I will read it to you slowly. It's level, comma, K-weighted, comma, against full scale. So it excludes any subwoofer components. The K-weighting curve is the opposite of the Fletcher and Munson curve, and I will show that to you in a moment. The K in and of itself has no meaning. It's the way the ITU assigns algorithm designators. So this was the next one in their filing cabinet, so that's where that came from. They added the true peak measurement in 2009, and that's really important because it allows us to operate much more aggressively than the industry thought was going to be possible. And again, we'll come back to the specifics of that, but here's what this thing looks like in a block diagram. So you've got all of the various audio channels coming into the algorithm, and you put them through the K filter, which is the opposite of what your outer ear does. You take then the average power measurement, and then you weigh the channels, and the reason for doing this is that our head for surround channels, the ear blocks, so that you have to weight the rear surrounds below the front and center. And then you get your measured loudness. So before we go further, this is probably something useful to make sure we all sort of are on the same page. Here's what we're talking about in sort of a waveform visualization. We have a noise floor, which is way down there. It's like, depending upon the bit depth, but if we're like, we're 24 bits, we're below 104, below full scale. The scale is not labeled correctly because that really should be 0 dB full scale. It was somebody else's drawing, sorry. And then between your operating level and full scale is your headroom, and your signal to noise then is measured both maximum based on full scale and operating point. And we realize that because the SNR does not change with operating point, that we can move things around in the operating range. So, but the peak measurement aspect is really important, not just from a standpoint of picking up odd impulse noises, but from a standpoint of understanding where we really are in relationship to clipping. Historically, this is what the manufacturers had done. They'd tried to make measurements based on the outputs of the samples. And the ITU committee realized that we needed to oversample. And what they came up with is a recommendation to do 4 times oversampling. And for you audiophiles, that's where 192 kilohertz audio sampling came from. That's 4 times 48. And then you can decimate down your samples and get a much more high-resolution result at 41 or 48 for CD. But it also meant that we had a reliable way of measuring where we were in relationship to clipping. And ATSC S63 came up with a recommended operating point of -24, and we were joined by the ITU in a document called BS 1864, and the EBU group that followed us by a year came up with a 1 dB difference, which is basically non-existent. So the other thing that we did as a group was to do a mixing test, and this was done quietly without the lawyers or the content managers ever noticing. One of the broadcasters collected material from his network and their competing networks quietly in a mixing room at USC. They covered the meters. They brought in some of the top mixing engineers in at least the LA area and asked each of them in terms to normalize the content. And the fader positions on the board were saved by the automation system. And then Tom Holman and students sat down and did the math and converted those to 1770 equivalent levels. And the results were the humans matched 1770. And the whole group sighed a collective sigh of relief because we realized that this really did work in the real world. But we also discovered that the EBU had asked the ITU to add a new function to 1770 that was termed gating, and I'll give you the details of that. In retrospect, this was as important an addition to the measurement system as True Peak, and here's why. First of all, here's what we mean when we talk about the gate. First of all, the last rightmost block that just says gate is an absolute gate to remove silence or background noise. And the other one, the 10 log 10, is a 10 dB relative, i.e. relative to the loudness coming out of the summation, to determine the foreground loudness, and that's a sliding window measurement. So you're operating on 400 millisecond blocks, updated every 100 milliseconds. And Remember that 1770 is an integrating measurement. So what that translated into is that periods of silence or low-level signals might result in a lower than perceived loudness measurement. And it was meant to be a refinement and not to replace any sort of anchor or speech element algorithms. We got some actual measurements of content courtesy of Canadian Broadcast. They had a server full of content, that's 100 and something pieces of content, and they went and did the 1770 algorithm without the gate and with the gate on the 100 and something pieces of content and discovered 86% there was almost no difference, half a dB. And gee, 5, 4, 3, this is beginning to look like a classic bell curve. Yeah, so here's what we talk about. In a waveform, you can now see what's going on. So the -2 algorithm, the gate, kicked open to measure content during the blobs of actual noise and didn't measure the silence. And we got about a 4.1 dB difference for this particular sample. Here's another one. But note, for example, those impulses over at the right end, those are important. We'll come back to them. But once again, they are included in the -2 and not excluded. But we still got almost a 4 dB difference. So people suggested with a digital audio workstation, let's just move things around in time and see whether it makes any difference. And so we did that, and it turned out, no, it made like 0.8 of a dB. So everybody said, I think we will go with a gate. Meanwhile, because remember, this was a real-time set of activities, in Europe, they created, out of the EBU, a group called PLOUD, and they were given a much broader scope than S63. They included radio broadcasters in addition to television broadcasters and recording studios and so forth. So a number of the operators wanted to see if they could come up with an automated measurement method so they didn't have a human involved. Other participants didn't want to rely on whether there was metadata or not because they didn't necessarily have metadata available. There were a large group of manufacturers that were each pushing their own competing technologies. And some of the broadcasters, as I said, wanted operatorless work. So the scope they were given is much broader, and I'll let you read the slide. And by the way, after we're done, Myra will put up a link to download a set of the slides so you can actually sit and read what their scope was. But it was not DTV-centric. That was an important thing. And it was heavily influenced by those manufacturers with their various competing methods of measuring loudness. They came up with a document called A128 in August of 2010, which is about 9 months after A85 had published. And they measured the audio signal on its entirety without emphasis on specific elements such as voice, etc. And that was a complete disconnect with what we had done, because the study is done, at least in North America, with real listeners in the room. The humans wanted to focus on the voice, but oh well. And they came up with a 1 dB difference in operating level. They also didn't like the LKFS. And I, for one, tend not to challenge the ITU unless there's some real grounds to challenge the ITU. They put in a request to the ITU that promptly got blocked by a couple of the nation participants, and that's the way the ITU works. So I will continue in this lecture to use LKFS unless it's a direct quote. A85. So as I noted it. We published the first edition in November of 2009. There were 2 updates posted in 2011, and there was an event in the United States Congress called the CALM Act, which I will talk about coming up. But that drove us to do a couple of minor updates. And then in 2013, because a number of the operators wanted the ability to deal with non-AC3 family codecs like AAC and DTS and so forth, we added provisions to deal with those. A85 relies on 1770 and recommended the adoption of 1864's interchange level of -24. It was written without any idea that the CALM Act was going to come down upon our heads. So before we get to the CALM Act, 1864 was a document written by the ITU to provide a worldwide program interchange without metadata operating point. And they picked -24. EBU, PLOUD, knowing that the ITU had picked -24 like we did, still went ahead and said -23. So go figure. One of the unintended consequences out of the PLOUD work is they published some fairly confusing documents. Unless people really understand the historical context under which they were created, you don't necessarily get the full picture of what you need to do as an operator, especially in dealing with digital audio. A85 goes much further into guidance, into setup and alignment of monitoring equipment, and A85 provides actually test sequences, so you can actually do this. But PLOUD chose not to do that, and they talked about metering and the operating range and some minor practical guidelines and so forth. And it was very loosey-goosey, in my opinion. Meanwhile, in Australia, events also happening in real time in different part of the world, Free TV Australia came up with what was called OP48, and they also came up with that -24 was the appropriate level. Like in the U.S., operators are expected to self-certify they're complying, and so are advertisers. And I note Australia liked LKFS. So Arribe also published a document. It's available in Japanese only. They also use 24 LKFS. So the CALM Act, I've alluded to that a bit. It was a seemingly short and appealing bill. How could anybody possibly vote against something that talked about advertisement loudness mitigation? And it became law in 2010. It required the FCC to prescribe a regulation to incorporate by reference and make mandatory the recommended practice A85 and any successor thereto. And as the chair of the group that owned A85, I just swallowed hard and said, what? Within 1 year. So we scrambled around. That's where the 2 minor amendments came up with, endeavoring to answer some of the questions we got from the FCC. But the unintended consequences of all of this is giving a standards development organization the power to produce a successor thereto for a recommended practice especially is just not where an SDO wants to go. And each of the 2 updates, the FCC did not always react in the way we had thought they would. We tried to spoon feed them some things. They came up with rules where they told the operators and the networks that they needed to self-certify, which was where Australia went at about the same time. And the other thing, the second bullet point, is that you can't distribute or discriminate in your certification. If you attach it to your program, you've got to make it available to anybody that has the ability to get to it. So we now have at least 3 countries with national level legislation on audio loudness. I hope India hasn't followed suit here, and if there's any ability for any of you to discourage your government from following North American, persuade them to not do that, because you don't want national legislation. You want the industry addressing these issues and keeping viewers and listeners happy. But, gee, then we got portable devices. And that started back before we got to digital, even, with this little thing called the Walkman. Some of you may remember that from earlier, followed eventually by a portable CD player called the Discman, and then from Apple we got the iPod, and now here we are. This means headphones. And remember the differences that Fletcher and Munson had measured at the low end of the frequency spectrum. So our ears do a special job of protecting us from impulse sounds, especially. So here's a word to us as users and listeners of the technology. Be careful with noise-canceling headphones, and especially those that seal into the ear canal. Those are marketed for, active people going to the gym, and they work probably very, very well, but you leave the listener exposed to loud impulse noises that might damage their eardrums. So be careful. The term portable doesn't only apply to young people, because I think that's sort of the classic illustration of, I've got a 20-something dancing down the street. I myself routinely listen to music via a portable device while I'm out walking. And the genre of the music is not important. It's the technology you choose. The consumer industry has largely ignored these issues, sadly. AES has not, thankfully. They have a couple of different documents that are available. One, a report that came out, half a dozen years ago, TD 1004. Senelec also wrote, and this actually carries the force of law in the European Union. Both of those may need to be purchased. AES, if you join AES as a student member, you may get it for free. So be aware there's 2 sort of physical categories for headphones, the over-the-ear and the in-the-ear. And the over-the-ear is typically what I wear on, for example, an airplane. In the ear, you have the not very well sealed one, the original earbuds, if you remember those. And then there's some semi or actually sealed in the ear, both the noise canceling and non-noise canceling. The newer earbuds don't totally seal, but they attenuate outside noise enough to where it could potentially be a hazard, especially in traffic. So be careful. You don't want to damage your ear and your hearing. You also don't want to get into a traffic accident or get hit. So what we can control as the operator of that device is our listening level. So let's pay attention to that. And it turns out that it doesn't much matter between whether we're streaming it or playing it back off a recording. Anecdotal evidence is that potentially people listening to recordings are going to be quicker to pause than folks streaming. So just watching people on the subway or out walking around city, I watch people on BART, which is essentially subway in the Bay Area, and the way they react when they get onto or off of the train, and you can see people going up in level or pausing. There's ongoing standardization work in this area. So to use an old American television slogan, stay tuned. And you should also look for a copy of AES 71, which came out in 2018, that covers streaming or portable devices as well. I will encourage you students to join both IEEE BTS, which is my sponsor, as well as AES and SMPTE. They all have student memberships available. AES, I think once you become a student member, you may be able to download free copies of the AES standards. I'm not sure. I know as a full member I can, but I think the student members can as well. And that brings us to questions, and we have hopefully about 10 minutes for questions. So Myra, do we have questions?
Yes, sir. So we have few questions from the participants, and the most asked is something: for encoding the original message, which type of device is preferred or is used?
It actually is, I think the question is much more related to not the encoding as much as the digitization. And the AES-3 standard process, you do the same digitization whether you're doing it at 41 kilohertz or 192. The thing about oversampling, which we also discovered in video, and so understand that actually most broadcast cameras, for example, oversample the video, was that you can do a process called decimation. And if you don't understand decimation and haven't taken a signal processing class, go take a signal processing class and you'll get to know all about decimation. But it's not just throwing samples away, it's interpolating between them. And you end up with a much better sounding result by doing decimation.
Right.
Encoding, hang on, just let me continue for a moment. Encoding from PCM into a compressed format is a also well understood process. It's lossy, so just be aware that we're losing bits. And some people complain about it being lossy, but we can't hear it anyway. Okay, next.
Thank you, sir. The next question is, how much tinnitus is serious problem in today's time, and how do we avoid the hearing problem and tinnitus in ear?
Oh, that's a good question. I am not an expert on the medical side, so I can't talk about how much tinnitus we have. But it's potentially a major problem. So one of the examples that I have in the discography, which is Mahler's Sixth Symphony, was the last live performance that we went to before we went into shelter in place. And it was the first of the Mahler's symphonies recorded, and it's the lowest in level. And I had complained in the very first time I gave this talk for an ATSC audience back, right after we published A85. Why was this so low? Well, I got the answer. In the fourth movement, there was a large object that was about 25 feet tall that a percussionist hit with a very large mallet that made a very dull but very loud thud. And that's why the recording engineer had backed off the levels so far, because that was a very loud thud. And I could see it coming because I could see the percussionist. But when I was listening to it off of the recording, you got surprised. So, yeah, that's where the impulse noise issue is something that we all, as listeners, need to pay attention to. So, next.
Yeah. Many participants have asked this question very frequently. It would be great if you could briefly explain the BS 1770 block diagram. So.
Oh, yes, we can go back through that again. And actually, I will do something that is extremely ugly and go into the show me all the slides. There we go. Come on, Outlook. There we go. Or not Outlook. PowerPoint. So we take each of the channels in the system, and recognizing now that we have people that are suggesting that we need to have 7 or 9 or 22 channels. So you would do this for all the channels in the system. And then you run them through the K filter, which undoes the effect of your outer ear. You take the average power of what was on that channel, and you apply a channel weighting factor that is based upon what your head does in free space with where the sound is coming from. Because it turns out not only does our outer ear play an effect in our hearing, but the shape of our head and the direction we're looking and so forth. But if we're looking straight ahead and, we're not looking around, so that we would hear stuff behind us down by several dB. We would hear stuff overhead. I think in some cases, if it's up to one side or the other, we might even hear it better. So I think it may get boosted. I would need to talk to actually the folks at CRC that are responsible for refining the algorithm going forward for all of the fancy new multi-channel audio schemes. But hopefully this makes sense. Next.
Okay. There's another question, sir, whether the CALM Act is still in effect or existence.
Oh, yes. It is very much in existence.
Okay. Moving on to the last question. Could you please give us a bit more insight on LKFS?
Sure. It is, as I said, and I'll even see if I can get the silly slide back up again, which has got the, there we go. There we go. It is level K-weighted, and that was the K-weighting curve was what was there on the block diagram, against full scale. So it's a very engineering, I mean, not what you would, if you went to a marketing person, this is not what they'd give you. This is what an engineer gets, right? We like 3-letter acronyms. We got a 4-letter one in this case. Level, K-weighted, full scale. That's what LKFS is all about. So.
Okay. Yes, sir. Thank you so much. That would be the end of Q&A session. I hope all the participants got their answers. Now, in the end of the session, I invite Dr. G. Rohini ma'am, Professor and Head Lab Affairs, to express her gratitude.
Yeah. Am I audible?
Yes, ma'am. Yes, ma'am.
Good evening, sir. Actually, it is
Good evening.
Good morning to you. Good evening, all. Now it's time to say thanks to all. On behalf of the Department of ECE, St. Joseph Institute of Technology, St. Joseph Group of Institutions. Life is worth hearing too, so protect your ear and hear and avoid fear. I feel proud and honored to spell the word of thanks to our guest speaker, Mr. Patrick Waddell, industry consultant and S6 ATSC chair, California, Chennai, for his inspiring speech on audio loudness. Thank you very much, sir, for sharing with us your words of wisdom on how to protect our hearing. My heartfelt thanks to our beloved chairman, sir, Dr. B. Babu Manoharan, for his consistent upkeep in the conduction of this program. My sincere thanks to our managing director, ma'am, Mrs. Jessie Priya, ma'am, and our director, sir, Mr. B. Sashishekar, for their guidance in conduction of the program. I would like to express my deep sense of gratitude to our principal, sir, Dr. P. Ravichandran, for his support to conduct this program. I also thank our head of the department and IEEE chapter advisor, Dr. C. Gnanakausalya, and all other faculties for organizing this event successfully. A special mention of thanks to our student chair, IEEE BTS Society, Mr. Nikhil Madhavan, and student vice chair, Mr. Selva Madhavan, third year ECE, and Mira, third year ECE, and Sanjana, third year ECE, and all other IEEE students for aiding in conduction of this webinar. Last but not the least, I would also like to thank all our participants for their active participation in this program. Thank you all. Thank you, sir.
You're welcome.
Yes.
Thank you, ma'am.
Um,
Again, I would like to take this opportunity to thank Mr. J. Patrick Waddell for joining us despite his busy schedule. And I would, on the whole, like to thank the department heads and each one of the IEEE staff coordinators, student coordinators, and EC staff members for making this event a grand success. Last but not the least, I would love to thank the participants for their active participation. A gentle reminder, the feedback link for this session is being given in the YouTube channel. Kindly subscribe to it and do fill in the details. That would be very essential for your e-certificate. And the details for tomorrow's SAVANT series is by our eminent speaker, Mr. John D. McDonald, who will be giving a talk on big data, IoT, enterprise data management, and new data requirements of drones and robotic inspection devices, which is scheduled at 3:30 p.m. Interested participants can register in the same link and attend the session. Thank you all.